Hi, I'm Megan, and I'm going to be going over the kth smallest value problem. Let's begin. So there are going to be 4 key points for today's agenda. The first one being to understand the problem statement. The second one being to brainstorming, most likely using pseudocode. The third, to solve the problem using our pseudocode. And the fourth is to, if we can, to improve upon our solution and make it more efficient. All right, so let's get started with our problem statement. Suppose you are given a binary search tree consisting of unique strings. Given the root of a binary search tree and an integer k, return the kth smallest value of all nodes in the tree based on alphabetical ordering. And as you can assume, by alphabetical ordering, we mean A, B, C, where A is the smallest letter or value, and then it just goes on from there. The constraints of our problem are the number of nodes in the tree is n. Each node in the tree consists of lowercase English letters. The requested integer k is at least 1, and same for the nodes n. So the number of nodes in our binary search tree will at least be 1. And our integer k that's requested will always need to be less than or equal to the number of nodes we have in our tree. So for example, we can't request the 100 smallest element or the 100 smallest value in a binary search tree of 10 nodes. The last constraint is that for each node that we have in our binary search tree, all of which consist of unique strings, the length of each string will be at least 1. So let's start with the test cases. Take a look at test case number 1. We have 3 nodes beginning with alpha, beta, and cat. So we have A for alpha, we'll do A, then we have B, and C for cat. So k is equal to 1, that's our target element, and that means we need the first smallest element in alphabetical order, which is alpha. So we return A, which happens to be the root of the binary search tree. In test case number 2, we have 4 nodes, and we have k is equal to 3. So we want the third smallest element in alphabetical order. So see, we have alpha and azimuth. L is less than Z. Take a look at these 2 letters. So we have A, and then we have L and Z. So alpha comes before azimuth, and then we have beta. So beta is our third smallest element according to alphabetical ordering. Okay. Now for test cases number 3, 4, and 5, they will be very similar. So you can take a look in test case number 3. We have 5 nodes in our binary search tree. The first node will be zebra, then bloom, zig, ape, and fancy. K is equal to 2, so we want the second smallest of all the elements in the tree. That element will be bloom, and that's because our first smallest is ape, and our second smallest is bloom, so we return bloom. For our fourth test case, we have mossy, 40, zap, empty, boost, accent, abort, and apple. We want the fifth smallest element, since k is 5, and just like in test cases 1 through 3, we end up returning empty because we go through this binary search tree in alphabetical order, or we find a way to sort it, and then we get empty, which is the 5th smallest element in alphabetical order. So we would have abort, apple, well, we would have actually abort, accent, and then apple, since we have B, which is less than C, which is less than P. And then we have boost, 4, and then we have empty, which is 5. So we end up returning empty as the 5th smallest element in our binary search tree. The same will apply for test case number 5, where we have igloo, doll, otter, air, eat, oil, and wolf. K is equal to 6, so we end up returning otter, which is the 6th smallest element in the binary search tree. So now that we've gone over some test cases, we're going to start brainstorming for our solution. One thing that'll really help us in this brainstorming process is taking a look at different types of traversals for binary search trees. There are pre-order traversals, post-order traversals, and in-order traversals. And as in order sounds, we are going to get our elements upon traversing our binary search tree in order. So if we have our binary search tree consisting of unique strings and we performed an in order traversal, we would end up getting it in alphabetical order like we wanted, so A, B, and C. This would actually give us everything sorted like we kind of want, and this is a hint for our solution, in order to get the kth smallest element. But if we used pre or post order, we would not get, upon traversing our binary search tree, a result or a number of nodes that are ordered correctly in alphabetical order. Or if we had integers and we started with 1, for example, and 2, we wouldn't get 1 as the smallest value or the first element in our in-order traversal. If it was an in-order traversal, we would. But if it's pre and post, we might have to perform an additional sort function in order to officially sort our nodes. So that's the benefit of using an in-order traversal as opposed to a pre or post-order traversal. If you were to use pre or post, you would have to work a little extra to sort your nodes that you already traversed through, giving you an n log n solution. And we don't want that. If you were to use an in-order traversal, just to let you know, that would give you an O of n solution because you're traversing the tree exactly once, and in the worst case, you're traversing all of the nodes to find the kth smallest element, or let's say push them back into a vector. Okay. So now that we've gone over in-order traversals, that's just a little hint at our solution and our brainstorming process. And like I said, if we perform an in-order traversal, we are going to get our nodes in the order, the proper order that we want in order to find the kth element, or in our case, the kth smallest element. So if we perform an in-order traversal and we get everything in alphabetical order, and we wanted to find the kth smallest element, an idea for this is to use some sort of storage container. So we'll take more of a look into that into our pseudocode. Okay. So for a pseudocode, notice that I have an empty vector named nodes. So imagine I had this little empty container, a vector. And I have a tree, and I'm going to perform an in-order traversal on the tree. As I perform this in-order traversal, I can push back my nodes that I visit, each visited node, into my vector, and eventually I will get my nodes in the binary search tree in order, in my vector. And once I have everything in alphabetical order, ABC order, I can actually just index the vector of nodes that I create from an in-order traversal, not a pre or post-order traversal, and upon indexing the vector of nodes, I can find the kth element, or the kth smallest element, that I want. And now that my vector starts from the smallest element to the largest element, I just have to index using k minus 1. And vectors allow for direct access, so our solution, or this portion of pseudocode, makes it a lot easier to digest. So let's get into our solution. Now back to our solution and using the pseudocode that we brainstormed to come up with the solution. So remember, in our pseudocode, I went over an in-order traversal as something that we could use to our benefit. And if I were to use an in-order traversal and traverse, let's say, a binary search tree, so let's go into, for example, we have sample test case number 1. And let's say I performed an in-order traversal on this binary search tree, I would want to store my node somewhere. So for that reason, I'm going to create a vector. And it will be a vector of strings, and I'm going to call it nodes. Okay. Now I want to perform my in-order traversal, and I want to end up pushing all those nodes into my vector. So I'm going to create a function for my in-order traversal. I am going to pass in my TreeNode node, and then I'm going to pass in my vector as a parameter, and it will be a reference so that the changes will be maintained. Okay. And remember, it's also a reference so I can avoid making copies upon every recursive call, because the in-order traversal itself as an algorithm is very recursive. Okay. So now that I have my in-order function started, I'm going to go ahead and write the algorithm for it. So I'm going to make sure the node that we are at is not null. And if it's not null, then I can go ahead and apply the logic of an in-order traversal to it. So this is where I use the recursive part of an in-order traversal. So I call the same function, and I'm going to go to the left node and then pass in my vector. And this is because, as you know, an in-order traversal starts from left until you can no longer go left anymore, and then the node to be considered, the current node, and then right until you no longer can. So it's left, current node, and then right. So after this, I am going to push back after traversing my left subtree, my current node to be considered. And after that, I'm going to recursively call in order again, and I'm going to traverse the right subtree. So that's my in-order traversal function. As you can see, I check if the node is not null pointer, and I traverse it in order going from left, the current node's value, and pushing that back into the vector that I created. And remember, it's a reference vector. And then I go to the right subtree. Now let's go back to our kth smallest function. I have my vector of nodes there. And what I'm going to do is I'm going to call my in-order function. I'm going to pass in the roots, and I'm also going to pass in my vector. Okay, except this will be like that. So now that I've called my in-order function, like I said, my vector is a reference. It's passed in as a reference. So once I'm back in my kth smallest value function over here, my vector is going to contain my nodes in order. So I can index my vector from here to get my kth smallest value. Okay. So essentially, I have created a vector. I've traversed my binary search tree. So for example, take a look at example 1. I traverse it in order. I push my nodes back using my in-order traversal into my vector that I passed in as a reference. And then in my kth smallest value function, upon doing my in-order traversal function, I actually index the vector. I don't iterate or anything of the sort. I index the vector itself to get the kth smallest value, or just the kth value at this point, because my vector now has the nodes in my binary search tree of strings in alphabetical order. So it'll start from the smallest node, the smallest value, to the largest one. Everything's in alphabetical order, so I can just index it from there to get the answer that I want. So let's go ahead and test this. So I have my main. I'm going to go ahead and create my vector. Actually, we won't need a vector. What I can do is create my tree. Instead of node, I'm going to have root. And then I'm going to use my insert function, that's just given to us, to pass in my roots and my next string, which is beta. And lastly, I'm going to have cats. And just as a little tidbit on the side, you can actually manually create your tree if you wanted by doing, for example, root right and then new TreeNode beta. But since we're given an insert function, I'm just going to use that and rely on it for ordering my binary search tree as needed. So now I have my binary search tree created, my nodes inserted for example 1. What I'm going to do now is actually I'm going to create a target variable. I'm going to set that equal to 1 since k is equal to 1 in my example 1. I'm going to cout and call my kth smallest value function. So I'm going to pass in the roots and I'm going to pass in the target. And we should get back alpha. Okay, so we got back alpha and our solution works. Let's try and trace through example 1 to see what we've done. Okay, So in main, I have my binary search tree, alpha, beta, and cat. That's my root right here. I have my target, k is equal to 1, or target is equal to 1. I call my kth smallest function, and I pass in the root of my binary search tree and the target value, which is 1. In my kth smallest value function, I have a vector of nodes, which is empty at the moment, but those will be the unique strings. I call my in-order traversal function. I pass in the root of my binary search tree and my nodes vector. When I call my in-order function, notice that I have my vector as a reference as previously stated. So any changes made to that vector, any nodes that were pushed back into that vector will be maintained when we go into the kth smallest value function again. So I perform an in-order traversal on my binary search tree. I push the nodes that are now in order into my vector, and then I just index the vector from there, return the value as a string from the kth smallest function, and then print it. And that's our solution. Now, the last step of this video is to see if we can improve upon this solution. So we're going to take a look at that next. So now that we've created our first solution, we want to see if we can improve upon that solution. So let's try and brainstorm for that. So remember that we used an in-order traversal as a major tool for our first solution. We found that if we traversed our binary search tree from the roots using an in-order traversal, we could push those nodes that are now ordered correctly by alphabetical order in a vector and then just index that vector to get the string that we want, the kth smallest element in that vector. So now let's take another look at an in-order traversal and see if there's a way we can still use this to improve upon our solution. All right, so we're back on in-order traversals, and what if, let's say, we still iterated through our binary search tree or traversed our binary search tree, but if we have k is equal to 3, or we wanted to find the kth smallest element, let's say we wanted to find alligator. So the first smallest element, which is k is equal to 1. So if we would traverse this tree using an in-order traversal, left, root, and then right, or instead of roots, we will say nodes since that is more appropriate. And we would go left and then left until we no longer can, for example, over here, and we would return alligator. So in our first solution, we would push back the word alligator into our vector of nodes. But what if we could just stop there and return alligator as our kth smallest element? What if we had k is equal to 2, and we continued our in-order traversal, and we went to bat, since that would be the next word we traverse to? Then we can stop there and return bat. So that sounds a lot more interesting and intuitive for another solution, an improvement. This would be an improvement because there's one major difference from solution number 1. That difference being the fact that we're not using a vector. We're not using any storage container at all. We're still using an in-order traversal, so we're still using recursion because we're going to use that no matter what. It's the easiest way to sort our binary search tree because we want to find the kth smallest element in alphabetical order. However, since we're not using a storage container, this improvement upon our previous solution will be more memory and space efficient. We're not allocating extra memory or using anything in addition to our in-order traversal. So we would just iterate through or traverse our binary search tree in order and stop at the kth iteration. We'd get our answer and then return that answer. That's simple. And again, the time complexity for the, let's say, the pre-order and post-order traversal, that was O of n log n. For the in-order traversal, it was O of n because we're traversing the tree exactly once in the worst case because we're visiting every node. And if we were to just use our in-order traversal and no vector at all, we would have the same time complexity, but for our space complexity, it would be a lot more efficient because we're not allocating any space for this solution. We're just using our in-order traversal, no extra vector. So let's go ahead and try and implement that. All right, so now that we've gone over a possible improvement upon our first solution, let's see if we can implement that. So I remember saying that I wanted to still use my in-order traversal upon my binary search tree. The only difference was that I didn't want to use a vector anymore, so I didn't want to allocate any extra memory or use any extra storage, so that my efficient solution would actually be more efficient. So since I want to do an in-order traversal, I'm going to go ahead and make a function for that. So I'm going to go ahead and have my in-order traversal function. And I'm going to have k, my target value that I'm looking for, as a reference. And that's because in our brainstorming part of this section, part of this video, what I was doing was I was stopping at the kth iteration. But to stop at that kth iteration, I need some sort of, let's say, a count variable. I need a way to know when to stop. And that's why I'm decrementing k. So I need to decrement k, and by the time I reach 0, I know I've reached that kth iteration. So let's say I want k is equal to 3. I would decrement k at each node to be considered using my in-order traversal, so in between the left traversal and the right traversal when I reach the current node. So I would decrement k there, and that's how I'm keeping count of when I'm going to reach my kth iteration. When that k finally goes to 0, then I will stop there and return the node. And it's being used as a reference because, again, my in-order traversal function is recursive. So I want this k value to remain the same. I don't want to make copies of it. All right, so we are going to do a TreeNode. Let's do the same thing as we were doing before. So I will have my same in-order function, and I am going to traverse the left subtree, for example. So you can take a look at example 1 over here and imagine traversing the left subtree. And I'm going to pass in k. So if the answer is in my left subtree, I want to store that just in case. And I'd know that the answer is in that left subtree. Let's say if it existed in my left subtree and that answer was not null pointer, then I'd know that was my answer. So I'm going to check if my answer is not null pointer. And if that's the case, I will return that answer. So that covers checking the left subtree. So let's take a look at, for example, example 3. We start with zebra, and we go down to the left subtree, and we check if our answer exists there. Our answer is bloom, so it does. Eventually, we will decrement k until we reach bloom and end up returning bloom. But how will we know when to stop at that kth iteration? So that's where decrementing k comes in handy. I'm going to put it all into one line. So what I'm going to do is subtract 1 from k first. That's what this pre-decrement means. This is the equivalent to doing this. Subtracting 1 from k and then checking if it's equal to 0. But I'm going to do that on one line, so decrement it first, and then check if it's equal to 0. So this is when we've reached a node to be considered for our in-order traversal, right after checking or fully traversing left. I will decrement k at that node to be considered, and that will count as one full iteration. Okay, and that's towards our kth iteration. So if k is equal to 0, then we know we can stop at that iteration. We know we've reached, let's say, the second iteration to get that second smallest element. So if that's the case and k equals 0, I'm going to go ahead and return node. Now let's say that's not the case. And this is still an in-order traversal, so we still want to continue right towards the right subtree if we can, and until we can. So in that case, I'm going to use the same answer variable. I'm going to traverse right. I'm going to check if the answer exists, and if it does, I will return that answer. Okay. So we're missing one more thing here, which is the base case. We want to definitely make sure, just like before, that our node we're at is not null pointer. So I'm going to wrap everything in that. And everything gets tabbed, so that's perfect. Okay. And if our answer doesn't exist in, let's say, the left subtree, I want to return null pointer. Return null pointer. Okay. So this is my in-order traversal. This is where a lot of the logic comes, because I'm just using my in-order traversal, and that's all. I'm not using a vector or anything of the sort. I'm just going to stop at the kth iteration and then get my answer and return it. So for my function, the kth smallest function, if my in-order traversal function is going to give me my answer at the kth iteration, what I can do is I can just return the node, and we will have, fix this, we'll pass in root and k. We will get the value of that, which will be a string, hence the string type. So this, for example, will return, let's say in example 3, this might return bloom. Okay, so now we've got our solution, and we'll go ahead and test that soon. Essentially, this in-order function, like I said, takes care of everything, our entire solution. It simply traverses our binary search tree, stops at the kth iteration by decrementing the k upon every node to be considered between the left traversal and the right traversal until you can't traverse left and until you can't traverse right. And that's why the logic exists here between lines 43 and 45. That's the main portion of our function, of this improvement of our solution. Okay, so what I'm going to do next is I'm going to start testing my solution. So I'm going to create my tree, keep it a pointer, and let's pass in example number 1, so it will be alpha as my root element. Then I'm going to go ahead and insert beta, and I'm going to insert cat, and don't forget to pass in the root. Okay. Now I am going to create a target, which will be 1 in example number 1, and finally I am going to see out my answer. I'm going to pass in the root and the target. And let's just double check what I should be getting here. I should get alpha, and that's upon this in-order traversal function checking if the answer exists in the left subtree, which it doesn't, and then checking if it exists in the right subtree, and if it doesn't, we return null. And same thing for the left subtree. So let me write some pseudocode for this function. So the answer So if the answer exists in the left subtree, return the answer. Okay. And all of that will be right here. If it doesn't, decrement k and return null. And if it doesn't, we will go on to see if the answer exists in the right subtree. And if it does, we return the answer. Okay, and notice we're only decrementing k in between or after the left traversal. All right, so let's go ahead and test this. Okay, so you can see I get alpha, but let's try one more test. Let's try example 3. So here I'm going to pass in zebra, bloom, zig, ape, and fancy. My target value will be 2, so I want to return bloom. I'm going to go ahead and run this, and you see that I get bloom. So once I pass in my root of the binary search tree and the target value of 2, target is equal to 2 or k is equal to 2, I'm going to go to my k at smallest function. I'm going to pass in the root and the target value, and I'm going to return the string or the value of the node, which is a string. And in my inOrder function, I'm going to check if the node, which will first be the root element, in example 3, is null pointer, which it is not. Then I can go forth with the logic that I have over here. Then I will traverse left, so Zebra's answer will be Bloom, which is not null pointer. So I will continue, and Bloom's answer is Ape, which is not null pointer. And once I reach Ape, you'll notice that I can no longer go left. So I'm actually going to decrement k, and then try to go right, which I can't either. And since I can't go right, we're going to start all the way at the top. So we're going to continue through this if statement. All right, so now that I have my solution or my improvement upon my first solution, I'm just using my inOrder traversal function, which is right here. And I'm decrementing k until I reach 0, which will tell me when to stop at my kth iteration. So let's go ahead and test this. So I'm going to create my main function, and then I am going to create my tree, starting with my root element. And let's do example 3, which starts with zebra. Then I'm going to insert Bloom, and then the following nodes. Let's go ahead and copy and paste that. Gonna have Bloom, Zig, Ape, and Fancy. After creating my binary search tree, I need a target variable, which in this case is k is equal to 2, so target will equal 2. And then I want to call my function that I created, and that calls the inOrder traversal function, which is k at the smallest. I'm going to pass in the root of my binary search tree in main. I'm going to pass in the target, and we will print what we get. So in this case, since k is equal to 2, we want the second smallest element in example 3, which will be, the first smallest will be Ape, and the second smallest will be Bloom. And when we run this, you can see that we get Bloom. So we're good with our solution. If we go up upon calling the k at smallest function, we call the inOrder function, so we rely on that inOrder traversal for the main part of our logic. But the root of our logic really lies here, between lines 45 and 47, when we're decrementing k until we reach 0, or we're decrementing k and then checking if k is equal to 0 in order to stop. So since we end up getting Bloom, what we do is since we're passing in the root, which is zebra is not null pointer, zebra's answer is going to be Bloom, and we're going to continue going down that left subtree until we reach Ape. But Ape does not have a left subtree, so it's null, and we skip this if statement and we decrement k. When we go back to Bloom, we decrement k again, so k goes from 2 to 1 to 0. And then we just return Bloom, so we return node. Okay. So that's mainly our new solution, our improvement upon our previous solution, in that we're just using a recursive approach. We're not using a vector. We're not using any extra space or memory. The time of our solution is still O of n, where n is the number of nodes, but the space complexity is clearly more efficient because we're not relying on the number of nodes exactly. We're not creating a vector or anything of the sort. We're just using an inOrder traversal. So those were our two solutions, and I hope you liked the video.